Very much, Shimon and Hussein, for the kind invitation, and also Tanya, I guess, to speak here in front of you. It's a great pleasure to talk about our work on highly charged ions. What will I be talking about? I will give a brief introduction into the motivation why we want to study highly charged ions. I will introduce the system to you, what highly charged ions are actually about. Briefly recap state-of-the-art spectroscopy in highly charged ions, then show you how we improve that by orders of magnitude using sympathetic cooling and quantum logic spectroscopy. We'll then briefly touch upon the argon 13 plus clock that we've implemented. And then the main part will actually be about searches for pit forces and dark matter using isotope shift spectroscopy. Okay, now we're assembled here because we know that something is fundamentally, that our understanding of physics is fundamentally incomplete. We don't know how to unify all four fundamental forces. We don't know what most of the universe is composed of because we don't know what dark matter and dark energy are. We don't even know why we exist because we can't explain the surplus in normal matter over antimatter. And if you look at these questions, an obvious approach would be to go into cosmology to search for answers to these questions, or high energy physics. But what this workshop is really about is that we can use the extremely high resolution in tabletop atomic physics experiments, the quantum sensors that we develop in the lab with 80 digits and more, to actually contribute to answering these questions. And my talk in particular will be about why highly charged ions are very good candidates for this quest. Now, if you think about dark matter, then you might think that this is a purely academic topic, that nobody else cares about dark matter. You're wrong. I was skiing last season, so I got these rental skis and they worked nicely. Yeah? And then I looked more closely at those skis, and in the back, you can see they have dark matter detonate. It makes perfect sense. Yeah, it's a feat of engineering. In the simplest ultralight scalar dark matter model, dark matter is Bose-Einstein condensate, so it's very cold. Yeah, it can act as a beautiful reservoir to damp all the ski excitement, mechanical vibrations. Now, intrigued by that, yeah, I started a patent search for dark matter, and you'd be surprised how many patents contain the term dark matter. Yeah, and this is the closest to this topic probably. It has 160 pages. One of the many reasons why I did not become a patent attorney. And it says here that it's postulated the dark energy and dark matter realize the coupling between the respective mechanical vibration systems and the electromagnetic systems of these quantum objects. And so right there, yeah, dark matter dampening works apparently, and it even comes with nice hand drawings. All right, we have slightly more or better motivated reasons to believe that there is dark matter, only slightly, yeah, because we still have no clue what it actually is. Yeah, so this is a table from Wikipedia, actually, where there are several dark matter candidates, roughly organized between wave-like particles and or wave-like nature and particle-like like dark matter. And with different quantum sensors, we can look at different regimes of these dark matter candidates. For example, if you do optical clock comparisons, you look for ultra light scalar dark matter particles in very extremely light dark matter particles, whereas isotope shift spectroscopy is more sensitive to electron to mega electron volt like dark matter particles. And I'm sure each of you has his own or her own experiment and can place them within this graph somewhere. Okay, now why are highly charged ions interesting in that regard? I believe that not too many of you have worked with highly charged ions before that, so let me briefly introduce them to you. When you start removing electrons from your favorite atom, then the scalings of your energy scales change. So the binding energy goes up like the square of the charge. Hyperfine splitting goes up to the third power. QD effects are enhanced by the fourth power, whereas Stark shifts polarizability effects are strongly reduced by the 6th power. So if you compare the hydrogen atom with hydrogen-like uranium, which is extremely highly charged, of course, then the binding energy goes to 140 kilo electron volts. Hyperfine splitting is in the optical regime in this case. And QED effects account for 300 electron volt of the binding energy of the last electron. That's why these systems have been very successfully used to test QED in the strong field regime. Just to make this more concrete, the first system that we investigated was iron 13 plus. It is a boron-like electronic structure, and the first dipole allowed transition due to the scalings here is now at 19 nanometers, whereas the fine structure splitting, usually at a few hundred gigahertz, is now in the optical regime at 441 nanometers. So to summarize, highly charged ions are strongly relativistic systems with large QED contributions. And you can find optical transitions in fine structure transitions, in hyperfine structure transitions when you go to hydrogen-like or lithium-like systems, and near lateral crossings, which is actually the most interesting case. Okay, now what can you do with these highly charged ions? First of all, since there's only very few electrons left, they're much better calculatable. Yeah? If you have 4 to 6 electrons or so, you can actually do fairly accurate calculations. Then, as already mentioned, they have been used in G-factor measurements to test QED, in particular in strong fields. They have the highest sensitivity of all atomic species to a variation of the fine structure constant and dark matter. That's because they're so highly relativistic and have a high ionization energy. Also because they're strongly relativistic, they have a high sensitivity to a violation of local Lorentz invariance. And since the electrons are close to the nucleus, you can use them to either study nuclear physics parity violation effects or isotope shifts, and that's the topic that I will spend most of my time on. Okay. Now, to address most of these fundamental physics questions, you need to turn your highly charged ion into an optical clock. And that's not so trivial. So first of all, what we want is for an optical clock is a very low sensitivity to resonance shifting effects. And highly charged ions actually have an advantage there because some of the shifts in typical ion clocks are strongly suppressed. For example, the second order Stark shift is strongly suppressed, and the second order Zeeman shift is also strongly suppressed, as well as the electric photopole shift. Yeah, and if you look at the other requirements needed to operate an optical clock, then these can also be fulfilled by highly charged ions. So we have narrow laser accessible transitions, fairly simple level structure, and that has led to dozens of proposals, some of which, or many, are summarized in this review, but in the meantime, they have come up many more. And so with highly charged ions, we now gain access to the third dimension of the periodic table, where sort of the first row is neutral atoms, the second row is singly charged ions, and then the highly charged ions are essentially most of the rest. Yeah? That animation, I need to speed it up eventually. Yeah? It takes forever. The message is there's a lot of highly charged ions with a lot of potentially very interesting features that have not been uncovered yet. Now, there's a state of the art in spectroscopy of highly charged ions. They're typically produced in a plasma discharge. Yeah? So we have an electron beam that has kilo electron volts of energy. It hits a gas of atoms, ionizes it, and then traps the atoms in a magnetic field and the electric charge of the electron beam. And then you can image the fluorescence that you have here using a grating spectrometer, for example, and get fairly high resolution spectra as shown here. Yeah, the only problem, this is in nanometers. So these lines are extremely broad because of Doppler broadening. They're split by the strong magnetic field of the electron beam ion trap. But due to the very strong signal to noise ratio, you can actually resolve these 50 gigahertz wide transitions down to 150 megahertz or so. And that's purely Doppler broad because the energy of the highly charged ions in the trap is electron volts. Yeah, and for us that's entirely the wrong unit to use. Yeah, it's megakelvins. You don't want that. Yeah, and that's the problem number one. Electron beam ion trap is a very noisy and hot environment. Problem number two is that most highly charged ions do not have suitable transition for laser cooling and internal state detection. And of course, then we cannot use the tools that we're used to from our quantum optics lab, and that's a problem. Now, problem number one we can solve by simply putting highly charged ion into a pore trap environment where we know we can achieve very high trapping frequencies or recoil-free absorption. We can have very long interrogation times. There's very few trap-induced shifts that we need to take account for. We can isolate them very well in principle, laser, cool, and so forth. And that's sort of the driving force behind ion-based optical clocks that have been demonstrated in the past already in many groups. Problem number two can be solved by using a technique developed by Dave Wineland and co-workers, namely quantum logic spectroscopy, where you can trap logic ion or cooling ion together with your spectroscopy ion in the same trap, and owing to their strong Coulomb repulsion Coulomb interaction, they form normal modes. They can use these normal modes to actually read out the spectroscopy information after performing clock interrogation, and you can prepare the internal state of your atom. And the transfer is accomplished through a series of laser pulses, yeah, where you transfer the internal state faithfully onto the, in our case, beryllium logic ion, where you can then detect. So in essence, this is a compound system where you combine the advantages of a very controllable species, namely the beryllium ion, with the interesting spectroscopic features of the highly charged ion. And the techniques that we're using here have been developed in the context of quantum information processing with trap ions. Now, highly charged ions are not the only application. The aluminum clock, for example, works on with the same technique, and we and others, at least, for example, at Basel and Zurich now, have also managed to improve our control over molecular ions using this technique. Okay, now to implement that, we teamed up with Jose Crespo's group at the MPIK in Heidelberg. He's an expert on highly charged ions and cryogenics. And together we designed and built this system that's now in my lab in Braunschweig. So since highly charged ions react very allergic against background gas collisions, we need a cryogenic vacuum. That's the only way we know so far how to get to the low pressures that we need. It's based on a closed cycle system, a cold head that and massive amounts of copper that conduct the heat away from the trapping region here in the 4K stage and the 40K stage all the way to the pulse tube cryocooler. It's all vibration isolated such that we have very small visible vibrations and an excellent vacuum background gas pressure. We then need a source for the highly charged ion. That's a compact electron beam ion trap based on permanent magnets, where we can have fairly large acceleration voltages of 10 kilovolts, large currents, and insert gases as well as solids using laser ablation. Now, once we have produced the highly charged ions in the electron beam ion trap, we can eject them. They fly out, are bent around the corner. We have a kicker electrode here, where we can do a time of flight separation of different charge to masses. We let our the favorite species through. We have a deceleration using serrated electrode decelerator here, and then they fly all the way to the pore trap, which is here in the cryo region. That's a macroscopic pore trap, gold-coated alumina, laser structured with very low heating rates. And in that pore trap, we prepare a laser-cooled cloud of beryllium ions, and then when we inject a highly charged ion, we observe it as a dark void, essentially in the ion crystal. Then we parametrically heat out the the remaining beryllium ions until we're left with a 2-ion crystal, which is the starting point for the quantum logic spectroscopy. And then I'm not going to go into the details on how that actually works. It's really just a series of laser pulses to transfer the internal state from the argon to the beryllium and then detect it there. I just show you how beautiful it works. Yeah? So this is a scan across the detuning of the argon fine structure transition here. And each data point is a repetition of 100 times roughly implementing this protocol. And this is a Fourier limited line width of 65 Hz. We can also do Rabi flopping on resonance. And then the decay that you observe here in the amplitude is strictly dictated by the excited state lifetime of 10 milliseconds in our 13 plus. Okay, now how to turn this now into a clock? Of course, for this you need to evaluate all possible systematic frequency shifts, and that's the hard part, of course. Yeah, getting this to work was sort of easy. Yeah, but then evaluating all systematics involves more time because you have to be super careful. Luckily for us, all the promises that the theorists have put forward in why highly charged ions should be excellent clocks have proven true. So this is our error budget. I won't go into the details, but there's a couple of remarkable things to notice. First of all, it's a very short table. Yeah, it doesn't contain 15 entries, but only 1, 2, 3, 4, 5, 6, 7. Yeah, and most of the shifts are actually 0 or at the 10 to the minus 18 level, and therefore you can measure them to at least 2 or 3 digits, and then get an uncertainty that is even lower than the shift itself. The only the limiting factors in our case are micromotion. That's a gigantic shift that we can measure down to a certain level. That has nothing to do with the highly charged state of the ion. It's a defect of our trap that we have not honestly understood yet properly. Yeah, so if you have any hints, I'd be welcome to hear them. We've implemented the 2nd generation, much more carefully designed ion trap. Yeah, it made the effect a factor of 3 worse. Yeah. So hints are welcome. But that's not a fundamental problem. There are ion traps without micromotion, yeah, and if we had one of those in the cryo system, yeah, then this shift would essentially go away, yeah, and with it, yeah, associated uncertainty. Now, the second shift is the AC-Siemens shift. That's if your clock light has not a pure polarization that drives only the clock transition, but has other components, then of course you introduce a Stark shift in your ground state. And that needs to be accounted for, and that's also an uncertainty that can be taken care of by using either pure polarization or advanced interrogation techniques like hyperresonance spectroscopy. These are now no fundamental limitations, and I'm hoping that the next incarnation of this highly charged ion clock will then be at 10 to the minus 18 or below. Okay, just to mention, yeah, the previously best known value of that transition frequency was on the order of a couple 100 megahertz, so we improved it by 8 orders of magnitude. So, of course, we compared our argon 13 plus clock to another clock. You have to probe the transition to verify that at least to some order, you can verify your error budget. And we were in the lucky position that we have an ytterbium octopole clock in Niels Huntemann's lab working in the building next door. And in this case, we used 2 frequency combs to compare the 2 systems. It averages down as expected. It's limited by the excited state lifetime of 10 milliseconds here. And we average down to about 10 to the minus 16 statistical uncertainty for 2 isotopes, compared the isotope shifted theory, and could confirm the so-called QED nuclear recoil effect for the first time in multi-electron system. And via the ytterbium octopole absolute frequency, we now know that argon 13 plus line is one of the best well-known absolute frequencies now as well. Okay, now I want to shift gears a little bit and show how we can actually turn this into something that helps us investigate new physics, namely isotope shift spectroscopy, and how we can use it to search for fifth forces. Let me briefly review isotope shift spectroscopy. you have two isotopes, A and A prime. And if you investigate the same transition in these isotopes, then you will observe a shift in their resonance frequency. This shift has two components. The first is the field shift. That is because the nucleus is not a point charge, but it has some extent that overlaps with the wave function of the electrons, characterized by EFI here. And when you go from one isotope to the next, then this nuclear charge radius will change, and therefore the interaction energy that leads to this field shift. The second one is easier. It's the recoil shift in the center of mass system, relative recoil between electrons and the nucleus. Since only the nucleus changes, it's also called the mass shift. Okay, and if you so what we don't like actually is the delta R squared, because that we cannot calculate. That would require QCD calculations. It's very hard. It's also very hard to measure using neutron scattering, for example. But we don't really like that. At least we don't know it with the precision that we would need to take advantage of this king plot of this isotope shift spectroscopy. And so what you can do is you can use two transitions, I, so that is the index for the transition. And so since this is a linear relation, you can use two transitions to eliminate the delta R squared from the equation. The way you do that is then you plot the two transitions in so-called modified isotope shift that's just multiplied with this factor or divided by this factor, the entire equation. Here you plot the modified isotope shift of two transitions, and as you can see here, that is very nicely linear. Now, what happens if we add an additional fifth force to the system? For example, relaxion or a dark matter candidate. Let's assume that field is promoted with sort of interaction carriers with mass m phi. It's represented in its simplest form as a Yukawa potential, as shown here with coupling constants YE and YN. That's the coupling of the field to electrons and neutrons independently scaled with a number of neutrons here, and then this Yukawa term. And so you can essentially combine that into a coupling constant for new physics to your system. Now, there's two components of that coupling. There's one, the overlap between the Yukawa potential and your wave function that's characterized by xi, dependent on the transition I that you're investigating. And there's a nuclear dependence, and its simplest form, it's just a minus a prime. That's the difference in the neutron numbers. Now, if you add that, then you will see you get this additional term that scales with a new physics coupling constants, the overlap of the electronic wave functions with the field, and the nuclear dependence when coupling to the nucleus. And then, of course, you have also higher order standard model terms that you have to account for. And therefore, if you make very high precision king plots and you observe a nonlinearity as indicated sketched here, then it could either be a new physics charge carrier or higher order standard model terms. And the problem is to distinguish between the two, of course. Okay, and what you need to do that actually is you need ideally two transitions of very different character. The very promising approach there we identified as using the fine structure transition in calcium 14 plus combined with the clock transition in calcium plus the S to D transition. Prior to our work, those two transitions here have been used for isotope shift spectroscopy, but they have a very common mode character, and so a very low sensitivity or lower sensitivity to new physics, as you can see here. So this is the sensitivity to new physics in a certain form, and here you can see just using these two transitions in single charge calcium, get this sensitivity, and the sensitivity is a factor of 3 or so larger in certain areas when combining one of these transitions with the calcium 14 plus transition. And of course, we're not the first one or the only ones doing that. There's many other works experimentally here in this field. Okay, so here are our preliminary results. We're just writing a paper on this where we have combined our calcium 14 plus measurements of all even stable isotopes, using again the frequency comparison against the ytterbium clock, and the result is essentially very similar to the argon-13 plus clock. The relative uncertainty here is in 10 to the minus 9 of the isotope shift in the end. We teamed up with Diana Craig and Jonathan Holm, who improved the spectroscopy data on the S to D 5-halves clock transition for single charged calcium. And we teamed up with Menno Dor and Klaus Blaum to measure the masses more precisely, because they were a severe limitation in our case. Now, if you now plot or zoom in to the data points, then you can see here the linear regression line. You can see here the points and uncertainty ellipses that are blown up by a factor of 1,000. Yeah. So we observe here now a king plot that is non-linear with 1,000 sigma or so. We're not the first to observe this nonlinearity. There's work in particular here by Vlada Vulicic groups in ytterbium and my colleague Tanja Mehlstolper, who also observed this nonlinearity in ytterbium. However, our work is complementary to theirs because we're limited by other standard model higher order effects. Okay, now what to do with that? Yeah. Okay, did we discover new physics? Probably not. Yeah. So there's a number of higher order contributions from the standard model. So this is the equation that I just already showed you, mass shift and field shift. Then there's a second order mass shift that you can actually calculate very accurately for calcium and calcium 14 plus. And then that makes up for some isotope combinations up to 99% of the nonlinearity contribution. And there's another effect that we knew was there, but thought what would be very small in calcium, because as you may know, calcium has magic and doubly magic nuclei, so you would expect perfect spherical symmetry. But what we see here is that nuclear polarization effects are extremely strong in some of the isotope combinations. You can factorize that again into a field contribution, the charge radius again squared, and then some nuclear contribution here that are unfortunately also weakly dependent on the electronic state. You have no clear separation between electronic and nuclear degree of freedom, which makes it very difficult to calculate, and also to eliminate from the King plot. Okay, just to give you an order of magnitude, for one isotope pair here, the quadratic recoil is 34 kilohertz of the isotope shift on the order of hundreds of megahertz. Nuclear polarization is 180 kilohertz, and all the rest is negligible essentially. And then these two are 2 times larger in calcium 14 plus, the quadratic recoil, whereas the nuclear polarization is 2 times smaller from very basic estimates. Okay, then to distinguish between these contributions and a new physics contribution, you can do a sort of decomposition plot to identify that. And for this, I need to introduce a vectorial representation of the isotope shift. So the goal is to identify the source of the nonlinearity in our system. These are the 4 isotope shifts that we have. And this is a nice linear set of equations that we can write in vectorial in an n-dimensional space, where n is 4 in our case, in so-called isotope pair space, where we have here a vector of the isotope shifts, we have here the unit matrix, and here a vector of the delta R squares. We can now add, and all of these lie in a plane essentially, where the big head here of the delta R squared means that there's a large uncertainty associated with the knowledge of the delta R squared. But obviously, those 3 vectors have to lie in a plane. We call that the King plane. If we now add the new physics term that I've shown you before, then we have this gamma here also as a vector, because it also contains the different isotope pairs, and that vector can be perpendicular to this King plane. And now all of a sudden, some of these delta mu vectors can come out of the plane, and then we know that there's some new physics going on, yeah, when they come out of this plane. That means that the King linearity is actually broken. We can also include standard model nonlinearities parameterized here in electronic degrees of freedom and nuclear degrees of freedom, again as in a vectorial form. And then we not only have gamma, but we have a more general vector that sticks out of the plane. And since we are in four-dimensional space, we have two vectors that can be orthogonal to this 2D King plane. And we call these vectors lambda plus and lambda minus. We can then express all these nonlinearities, yeah, the additional fifth force and the standard model nonlinearity contributions within that sort of, again, two-dimensional space spanned by this lambda plus and lambda minus to be able to identify or shine some light on the origin of these effects. This is the in-plane contribution, and this is the out-of-plane contribution, where any data point that you measure will be characterized by this vector combination of these lambda plus and lambda minus vectors. So we have done that. This is the result. Here is lambda plus, here is lambda minus. Let me walk you through this. We have here, the cross here is our experimental result. We have the second order mass shift that we can calculate fairly accurately given by the small error bar here. And we can, since we can calculate it accurately, we can subtract it. Yeah, if we subtract it from here, we end up in this orange block here that then inherits, of course, the uncertainty from the calculations. And then the second standard model contribution that we have is a nuclear polarization, which is this green dot associated with an extremely large uncertainty. Yeah, and that's why we have this large uncertainty ellipse, because our model of the nucleus is just not good enough. The new physics, by the way, the fifth force would lie along this line. Yeah, but since we don't know where the nuclear polarization vector would lead us to, yeah, we don't know if there's going to be a residual lying on this line or not. Yeah. Currently, with the uncertainty that we have, it's compatible with just standard model physics, essentially. Okay. So there's another step that you can take, which is called a generalized King plot. You remember we did the King plot in the first place to get rid of the delta R squared term by combining two transitions. We can play that trick again for the other higher order nonlinearities by also using more transitions and more isotope pairs. And so this is a parameterization that I showed you before already. And if we now use n transitions and n isotope pairs, then we can eliminate further the standard model parameters beyond the delta R squared here. And what we did now is we used the calcium protein plus transition, the calcium crop transition, and the fine structure splitting transition in the D state that has been measured by other groups, also to a fairly high accuracy. And doing all that, yeah, so let me explain you, yeah, so we have 50% uncertainty in the nuclear polarizability, that was the large ellipse. We have 10% uncertainty in the sensitivity calculation. We have 10% uncertainty in the second order mass shift calculation, which has been subtracted from the data. And then if we do a generalized King plot to take out other higher order standard model contributions, then we arrive here at this red line, which is slightly below the previous best value established by the ytterbium measurements, but ever so slightly. It's probably marginal at this point. But it's the best current bound compatible with our data and the other data from physics. to improve on that, we need better calculations, and in particular, we need a better model for nuclear polarizability. If you know somebody who's an expert in the field, please tell me. We're eager to cooperate on this. With that, I'm at the end. I hope I could convince you that highly charged ions are a very interesting species to work with. We have achieved full quantum optical control of highly charged ions, demonstrated an optical clock, and put new bounds on fifth forces using isotope shift spectroscopy. We're now investigating new clock candidates that are better clocks and eventually also have a high sensitivity to alpha variation to probe in this ultra light scalar dark matter sector. And since most of the infrastructure in our lab is concerned with the logic ion, it's very easy for us to change the highly charged ion. We just need to put a new sample in the EBIT by a spectroscopy laser, and then we can go ahead. Thank you very much for your attention. And I would like to acknowledge the exceptional great work of my team in the lab, also Kresslers group. These are now 2 generations of postdocs and PhD students. And if you want to join this type of effort, please let me know. Thank you.
Okay, thanks, Pete, for a great talk. We do have time for a quick question. I'll quickly address the questions you have about people to contact. So for nuclear polarizability, Sonia Baca at Mainz, she does nuclear theory related to nuclear polarizability. And in some of these systems, you can actually measure it. It's hard, but you can actually measure it. For the micromotion in the Paul trap, so we used to see this years ago. For us, it was dependent heavily on the injection optics of the ions as you inject them into the Paul trap.
We removed all that.
Okay, so
we don't change a thing.
We never ended up doing things at this level of precision. But the 2 people, I mean, Klaus Blum would be one person to talk to about this.
He doesn't know about micromotion.
Okay.
He uses penning traps.
And the other one would be the beta decay Paul trap at Argonne National Lab. And Guy Savant.
I think there's probably enough ion trappers in this room that I want to chat with, to see if some insight. And we suspect it's some because we have traps of this type in room temperature setups that are just fine. So we suspect that when cooling down, the trap geometry changes. That's the only viable explanation we have at this point.
And then the last thing is, have you at all tried? Have you at all tried doing things with long-lived radioisotopes?
No.
Highly charged radioisotopes?
No, not yet. But a former student of mine, Peter Schmidt, he started his own group at GSI in Darmstadt, and he's going to do that.
Okay.
So on this generalized case plot, I will show this 2-dimensional dominant carbon minus. So I was wondering, why is the standard model, beyond standard model physics aligned there, or shouldn't this be assumed, or?
What do you mean?
The new physics, why is it actually aligned?
So you can sort of calculate the xi coefficients, for example. You have the gamma coefficient, and then you can look where that would lie in, and what we don't know is the alpha and p, the coupling strength. And that's that parameterizes the position on this line. That's why it's a line, because we don't know the coupling strength.
Thank you very much. Can you elaborate a little bit more of nuclear polarizability theory? Only to a certain degree you can trust. In the end, it will have to come from experiments. And what type of experimental measurement, the community can help you, for example, to pin down this parameter value?
Well, I'm afraid we are probably the most accurate measurement of nuclear polarizability of calcium at this point. I would turn the argument around. We can now help nuclear theorists, to develop their models to the extent that they agree with our measurement. Okay. Assuming that everything that we see is the remaining part is coming from nuclear polarization.
In order to make more improvements on standard model or beyond standard model physics, you need somebody else to do the nuclear polarizability.
I fully agree, yeah, and I'm no expert in nuclear polarizability measurements. I'm not sure if they can come close to what we're doing here
I see.
in terms of accuracy. However, we can push the generalized steam plot further. That takes out anything that is factorizable between nuclear and electronic contributions by using more isotopes, maybe radioactive isotopes, in more transition.
Maybe Jimmy can start setting up and I can use my initiative as chair to also ask a question. It seems like the other thing you could do is combine your isotope shift measurements with, say, ytterbium and all the other ones in the hopes that, well, all the nuclear shifts will be giving you like different nonlinearities. New physics would presumably give you this sort of same nonlinearity.
Yeah, I think only once you see a nonlinearity that standard model cannot explain, that type of approach will be useful, because the entire king plot technique hinges on the fact that the nucleus is always the same, and therefore to a certain extent can be factorized out of the equation. And if you start now adding ytterbium, yeah, then I would not know how to plot that into the same graph. Yeah. Of this type.
And I mean, I guess the other thing that people in ytterbium are doing are adding more and more transitions, of course, but I guess you're somewhat limited in that unless you start stripping more electrons off.
Yeah, we have other highly charged ions, there's calcium 15 plus, but there would need to be a very good physics case, yeah, for us to do that.
Let's thank Pete again.